In this video, we're going to cover how to find the horizontal and vertical tangent lines when we're doing implicit differentiation. Let's jump in. Okay, so here we want to find the points on the implicit curve where the tangent line is horizontal and vertical for this equation. Go ahead, pause the video, and see if you can figure that out. Okay, so here are the answers. The tangent line is going to be horizontal at 2, 4 and 2, -2, and it will be vertical at 0, 1 and 4, 1. So if you already understand that, feel free to skip this video. Otherwise, we're going to explain exactly how we got these. So think about what we're trying to find here. We're basically trying to find whenever the tangent line is horizontal or vertical. If we have a horizontal tangent line, hopefully that makes sense, that would be a slope of 0. And if we have a vertical tangent line, that would be a slope of infinity. And if you think about it if it was like a slope of 10,000, just a gigantic slope, it would be like almost vertical, or it would be really, really high up, really, really high slant or slope. So like in the limit, as the slope goes to infinity, hopefully it makes sense that it would be perfectly vertical. So what we're trying to do here, remember, is to find the slope or the points where the slope of the tangent line is 0 or infinity. So we need some equation that tells us the slope of the tangent line. What would that be? Think about it for a second. Hopefully it makes sense that that would be the derivative. Now, the fact that we're doing implicit differentiation doesn't change anything. The derivative is still the slope of the tangent line. The only difference is that we have to use implicit differentiation for this specific implicit curve rather than explicit differentiation. So let's do that. Let's take the implicit derivative. I've already kind of dug deeper into the theory behind implicit differentiation in other videos. I won't rehash that here. Basically, I'll just apply it. But if we're taking the derivative of both sides with respect to x, this is essentially what we would do. So derivative with respect to x of the left side, and also derivative with respect to x of the right side. If you have a true statement, if you take the derivative of both sides, you will also get a true statement. So here, what's the derivative of this? Hopefully it makes sense, and that would be 18x minus 36. And then here's the implicit part. That'll be plus 8y dy dx minus 8 times dy dx equals 0. So there you go. And again, if we're really trying to find the implicit derivative, we need to get all of the dy dx's on one side, and we need to get all of the everything else basically on the other side. So how would we do that? One thing we can do is add 36 and subtract 18x to the other side. So we'll get 36 minus 18x. And then we'll be left, think about what we'll be left with. We'll just be left with this. And then what you can do is you can factor out, if you will, think of it like kind of using the distributive property in reverse. You can effectively pull that out, the dy dx. Remember, dy dx is what we're actually trying to find, but you can pull that out. So you have 8y minus 8, and then that will still equal 36 minus 18x. And then finally, we can just divide both sides by 8y minus 8. So we'll get dy over dx equals, and also I can pull out an 18 here. Hopefully that makes sense, and I'll just get 2 minus x. And then also I can pull out an 8 from this, and I'll apparently just get y minus 1. And you could simplify this a little bit further if you wanted. So you could say that, dy dx is equal to what's 18 over 8, or how can we simplify them at least? They're both divisible by 2. We know that, so that'll be 9/4. And I think that's the most we can do. So yeah, that'll be 9/4, and then 2 minus x over y minus 1. So there you go. This is the implicit derivative. Now, how do we actually use it to find the points where the tangent line is horizontal or vertical? Remember what we said before. In order for the slope of the tangent line to be horizontal, this slope needs to be 0. So in other words, the derivative here needs to be 0. When would that happen? Hopefully it's clear that the derivative would equal 0 here whenever the numerator is 0, and specifically when the denominator is not 0. When is the numerator 0 here? Hopefully that's clear when x is equal to 2. So basically we'll have horizontal tangent lines. Horizontal when x is equal to 2, because that'll cause dy dx to equal 0. And then for vertical, when will we have vertical tangent lines? Think about it. That would actually be when the denominator is 0, because loosely speaking, 1 over 0 is infinity. It's not really, it's undefined. But in the limit, specifically the limit as the denominator gets closer to 0, the slope of the numerator approaches infinity. That's a more accurate way of thinking about it. But either way, that's going to happen when y gets really, really close to 1 or equals it. So these are kind of our two constraints, so to speak. Whenever x is equal to 2 on the implicit curve, we should have a horizontal tangent line. And whenever y is equal to 1 on the implicit curve, we should have a vertical tangent line. But again, this problem didn't ask for the x or y values when it happened. It asked for the exact point, so like x comma y. So we still need to find that. So let's think about how would we do that. Go ahead and pause the video and see if you can think about how we would address that. In order to figure out the exact points where this happens, we need to plug these constraints into our original equation. Remember, this was the original implicit curve. And basically what it's saying is that whenever x equals 2, those will be the coordinates, or those will be the coordinates, I'll say, of the points where the tangent line is horizontal. So let's do that. Let's actually plug that in. So if we're trying to find the horizontal case, so let's think about that first. So horizontal. So we'll get 9 times 2 squared minus 36 times 2 plus, I'll just leave 4y squared minus 8y plus 4 equals 0. And let's think about what we get. So 2 times 2, or 2 squared, would be 4. 9 times that'll be what, 36? Minus 36 times 2 is minus 72. And then all this stuff stays the same, actually. So plus 4y squared minus 8y plus 4 equals 0. And we can actually simplify this a little bit further. So 36 minus 72 is negative 36. And then if we add 4, that would be negative 32. So hopefully it makes sense that this whole thing becomes 4y squared minus 8y minus 32 equals 0. Now think about what this is. This is effectively a quadratic equation that we can solve, hopefully, just by factoring. So, or by guessing and checking. So if I pull out a 4 here, all these are divisible by 4, so all these coefficients are. So I'll get y squared minus 2y minus 8 equals 0. So which two numbers multiply to 8 and add to negative 2? Hopefully it makes sense that y minus 4 and y plus 2 would work, if you think about it. Negative 4 and positive 2 add to or multiply to negative 8, and they add to negative 2. So what does this mean? It basically means when y is equal to negative 2 or 4, that would satisfy the condition of x equaling 2. Remember, we originally, in order for us to have a horizontal tangent line, we figured out that the numerator would have to be 0, which basically meant that x would have to equal 2. And apparently, the only two y values where x would equal 2 are negative 2 and 4. Therefore, for the horizontal for the points where our horizontal tangent line is on this curve, it would be basically 2 comma negative 2 and 2 comma 4. So this x value, and then it could be either of these y values that would satisfy the equation. So there you go. That's half the battle. Now remember, we need to do a similar thing with the vertical ones. So let me copy that down. If we're trying to find the vertical points, this, that's going to happen whenever y is equal to 1, we've already established. Because remember, when y equals 1, that causes the denominator in the derivative to equal 0. And if the denominator is 0, that basically means the slope is infinity. So now we can plug that in and see what happens. So we'll get 9x squared minus 36x plus 4 times 1 squared minus 8 times 1 plus 4 equals 0. And let's see what we get here. 9x squared minus 36x plus 4, that makes sense, minus 8 plus 4 equals 0. So this stuff actually cancels out. And you just get 9x squared minus 36x equals 0. And then you can think about what would cause this. So one thing I can do, I can factor out a 9. I can actually factor out a 9x, and I'll be left with x minus 4 equals 0. So hopefully it's clear that x equals 0 and 4 would work here. So whenever y is equal to 1, remember that was the condition above that caused us to have a vertical tangent line whenever y is equal to 1, but y can only be equal to 1 on the curve when the x values are 0 or 4. So basically 0, comma 1 or 4, comma 1 would work here. So these are where these should be the points where we have a vertical tangent line. So hopefully all that makes sense. Apparently, and actually let me just consolidate everything real quick. So hopefully, let me pull this down. What we just found was that on this curve, this is where we have horizontal, or these are the points where we have a horizontal tangent line. And these are the points where we have a vertical tangent line on the curve. Remember the original curve, this implicit curve. So apparently that's the answer, but the question is, why is that the answer? Or why does that make sense? Let's take a look at it in Desmos to see if it makes sense. So the question is, do the answers that we got make sense? And the answer is actually yes. One other interesting side note here is that apparently the function that we've been dealing with this whole time has been an ellipse. Again, we didn't really know that. We didn't need to know that. But yeah, just as an interesting aside, if you completed the square on the x and the y terms separately, you could have algebraically manipulated it into the form of an ellipse that you're used to. So we didn't do that. We didn't have to know about it, but yeah, like it was an ellipse. Again, we didn't need to know that to actually solve the problem. We were able to do that without having any idea that we were dealing with an ellipse. But yeah, apparently this whole time it was an ellipse. So that's that. And now the question is, do those points make sense? Remember what we said. We said that we have a tangent line that is horizontal at the points 2, comma 4 and 2, comma negative 2. So let's see that. If I go to 2, comma negative 2, that would be down here. And you can see, yeah, that actually is graphing a horizontal tangent line. And if I go around the curve up to here, up to 2, comma 4, yes, that's also horizontal. So those 2 points actually are where the curve is horizontal. So that actually does make sense. So that's interesting. And remember what we said about the vertical tangent lines. We said that happened at 4, comma 1 and 0, comma 1. So think about what's 4, comma 1. That would be right here. Yep, that makes sense. So it is vertical, actually. And then if we go all the way around the curve to 0, comma 1, yep, it makes sense that that's also vertical. So this is the geometric interpretation of what we found. Again, the derivative still means the equation or the slope of the tangent line at each point, even if we're dealing with implicit functions. It's just that the way we have to find it is a little bit different with implicit differentiation, but it still means the same thing. And as a side note, as a bonus, we can actually figure out the points on a curve. We can figure out the points on a curve where we have a vertical tangent line, which is not something that we could have do before with explicit derivatives. There's a deeper reason for why that is, but yeah, we kind of are able to do a few more things than we can with normal differentiation if we're using implicit differentiation. So there you go. Hopefully that all makes sense. If you have any questions, leave them in the comment section. Otherwise, I'll catch you next time. See you.